scene. So we will run this first image segmentation with a unit-like architecture. So what is a unit? If you just type unit, you will find out unit is a convolution neural network in which you input an image and you output also you get as an image. Okay, so you can do various things, like you can do some kind of remote sensing or weather prediction using unit. You can have it as an regression problem, image to image regression, wherein in between the operations that are having that are being done are convolutions, or you can have it as a segmentation problem. So in segmentation, basically you rather than just identifying, for example, in this image whether there is a cat or not, you also have to identify the each, so you have to classify each and every pixel based on their classes. So you can see that this purple is a particular type of cat, then this brown is another cat, and then this green is maybe some matte, and then black and this blue is are the other backgrounds. So we will see the image segmentation task with a unit-like architecture. So the data set that we will be using is Oxford Pets data set. So you can just see this Oxford Pet data set. So this Oxford Pet data set looks something like this. We have a cat, we have a dog, and then so these are your inputs and these are your labels. Okay. So that's the Oxford Pet data set. Yeah. So you can see this. It's a label data set with all these around. Looks like a balanced data set with equal number of breeds, and okay. So this data is getting downloaded here. So now, yeah, we can see that this data has now been downloaded. So we have also untarred the images.tar.gz and annotations.tar.gz. So what you have is, so you can see the annotations. So in the annotations you have, okay, we'll add one more cell here. So you have annotations, images. So let us see what is in the images. So you can see that there are these, let us see, it works. No. So there are these files, okay, which correspond to this, like these are the PNG file, JPG files, and then let us see what is there in annotations. So you have list.txt, test.txt, train.val.txt, and so these are the files you have. And there is this another folder, try maps. So so these are your labels or the annotations. So in these files, in these images, each pixel will be labeled as a class. Okay, so you can see this is the input directory and this is our target directory. Then the image size, you can maybe read a file and see, or what we maybe want to consider is 160 by 160 by 3, and the number of classes is equal to 3. So that is what we are considering here. And the batch size we are taking as 32. So now you sort these images. So this is a list of the image path, input paths, input image paths. This is the list of target image paths. So you just join the so you have the input directory and the target directory. So you concatenate the path of each file, and then let us check how many number of samples are there. So number of samples is 7390, and so you can say, so for input path, target path, and zip. So you just take the first 10 uh, input path and target image paths just to check whether, because we have sorted, and it should not be there should not be any mismatch. So you can see that we are getting proper inputs and the labels. Now, what does one input image and corresponding segmentation mask look like? So you get this display and image function from ipython.display, and so let us display the image input 7 and display the auto contrast version of the corresponding target. So this is the target image path. So you say image img equal to pil dot image ops dot auto contrast. So let us see how they look like. Okay, so this is your image, and this is the segmentation. Okay, so you can see that all the black is basically the wherever the cat is, and rest all is white or gray. So we can also see what is there in the data. So img, let us see. So img is from this pil. So let us maybe say image. So just plots the image. So this is your input image file. Let us see how to uh, image to numpy. Okay, so image array is equal to np dot array. Sorry, let us define numpy. Okay, so yeah, you can see that this is your input image. These are the values it has, and we can even say print. We can dot max dot min. So maximum value is 255, minimum value is 0. Now let us see what is there in the target. So to read this, oh, this was your target image, and then this was your input. Okay. So this is your input image. Okay, yeah. So yeah, this is your input image, and this is your target. So wherever you see 127, I think that's somewhere between black and white. So that is gray, something like gray. And wherever you see 0, so it is white. And wherever you see black, it is 255. So this is the output that we want, and this is the input that we have. So now you have to prepare a sequence class to load and vectorize batches of data. So we are making this data loader. So I don't know if we have discussed this before. Data loader. Yeah, so okay, this is PyTorch data loader. And this is Keras. And okay, I think this is fine. So data loader is basically when you load a lot of data to the memory, and yeah, so and then what you would want to do is that data for training, it goes to the GPU. So like this kind of communication between the CPU and the GPU, or loading it from the disk, that sometimes becomes an IO bottleneck, and you will maybe if there is some memory leak, so you would find out that you are getting some memory error, because that leaked memory that will keep accumulating, and then you will get some random memory error. So a better way is to basically create a data generator. Now a data generator, when you create, so this is a standard, like the from scratch if you want to create a data generator, but you can these days using TensorFlow and PyTorch, you can just directly make a data generator. So you can see that so these three functions, underscore underscore len underscore 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 get item and on epoch end. So these are the three functions that you should have. And yes, and this is a class, so you will have the init function, and you basically so data generator class, it's a derived class of, it's a child class of keras.utils.sequence class. And this I think in, yeah, so this one has should become now. So Keras has become a part of TensorFlow since TensorFlow 2.0. So if you want to access Keras, you just say tf.keras rather than saying Keras directly. So you can see that we have these three functions here: init, len, and get item. So init, and we also have on epoch end, but they are not defining it here. Okay, fine. So the init function will basically just initialize. It will define the constructor for the class. So what is the batch size? So these are the arguments that you will give when you will make an object of this class Oxford Pets. So what is the batch size, input image paths, and target image paths, and the length of the basically the length of the or the number of the input image paths and target image paths. And then you have the underscore underscore get item. So this will, every time you call this function, it will return you a batch of the input and the target label, target data. So let us run this. We have defined the data structure. Now it's so what they're saying is we'll prepare a unit exception style model. So let us see the architecture of this exception style model. So you can see this uh, exception style section architecture. Okay. Yeah, this is the exception network. So we have already seen that in we have seen an inception net, right? If you remember, we were talking about inception nets in which we have in each layer, in between each layer, we have all the different types of filters. So rather than just having a filter of one one size, we you can have multiple multiple size filters. So that is the network we are going to use. And so first, yeah, we will say tf.keras here. And okay, so you import this layers class from tensorflow.keras, and you have an input of the shape, image size, and +3. So you will have, so this image size is 160 by 160, if you remember from, so we have defined it here, and it says +3. So this will be comma 3 because we have 3 channels. So we first make this input layer, okay, which takes in the input of shape 160 by 160 by 3. Then you do a con 2D operation with 32 filters, each filter of the size 3 cross 3. Number of strides are 2. The padding is same, and you pass the inputs to it. You perform batch normalization and ReLU activation, and keep this aside for residual purposes. So we will use this previous block activation further. Now what you do is you make these downsampling block. So these are the downsampling blocks. So you say for filters in 64, 128 to 56. So these are basically the number of filters in different layers. So the first we have activation, ReLU activation. Then we have this separable con 2D. Okay, so this I think is for the exception network. So it says separable con 2D, it's a depth-wise separable 2D convolution. And separable convolutions consist of first performing a depth-wise spatial convolution, so which acts on each input channel separately, followed by a point-wise convolution, which mixes the resulting output channels. So the depth multiplier argument controls how many output channels are generated per input channel in the depth-wise section. So intuitively, separable convolutions can be understood as a way to factorize the convolution kernel into two smaller kernels, or as an extreme version of inception network. So this we are will use this separable con 2D. Let us see if we get some visualization. So we'll see how this separable con 2D looks. So Yeah, anyway, this is okay. So this is a normal convolution with 8 cross 1 in output, and you have this filter. This is a 3D filter, and so this is a normal convolution with 8 cross 8 cross 256 output. So in this case, if you take 256 kernels, so you have 256 as the third dimension, as the size of the third dimension. Now in depth-wise convolution, so in the first part, depth-wise convolution, we give the input image a convolution without changing its depth. So we do so by three kernels of shape 5 cross 5 cross 1. So you see you have this input of shape 12 cross 3. So these three are the channels. Now you apply these kernels of which are 5 cross 5 cross 1. Now each 5 cross 5 cross 1 kernel iterates one channel of the image, getting the scalar products of every 25 pixel group, giving an output of uh, 8 cross 8 cross 1. So this will be 12 minus 5 is 7 plus 1, which is 8. Stacking these images together gives you 3 by 3 8 cross 8 cross 3 image. Now what is a point-wise convolution? So in point-wise convolution, so this original convolution, you see we got 8 cross 8 cross 3, and so this one you will convolve using this 1 cross 1 cross 3 filter. Okay, and the result that you will get is 8 cross 8 cross 1. So this is what a basically your separable con 2D operation is. So that's what we are doing here, and we are saying what is the number of filters, and this is the number of channels. So let us see. Yeah, what is the second thing? Yeah, that's the kernel size. Sorry. Yeah, that's the kernel size. And okay, okay. So this is your layer one, not layer one, but layer one inside this block, inside this downsampling block, and then this is your layer two, and then this is your layer three in that. So then you will use the you will use the previous convolution. So you will use this the output of your first layer, like the layer at the beginning, and you will perform a con 2D operation on that, so with 64 filters, and you will just add this x and the residual. So this is the skip connection, this is the residual connection that we have, and then you keep this so for this also, so this x also you save, and then it goes on to the next set of number of filters. And so this is so the then the next step is going from higher number of filters to the lower number of filters, and you can see that we are using this con 2D transpose. Oh yeah, basically which will increase the size of your input, whatever input size it will get. And so if you want to see con 2D transpose, there are very nice visualizations of what exactly is con 2D transpose. So you can see this. So this basically increases the size of your input. So in this case, you see we had a 4 cross 4 input, and the output is 1 2 3 4 5 6, a 6 cross 6 output you have got. So that's what con 2D transpose does. So we are increasing the size of the input images, and yeah, because this led to this kind of this block led to a decrease. It should actually lead to a decrease, because we are using the padding as same, but the stride is equal to 2. And then again, so if you do this, like and before that also we had done convolution with strides equal to 2 and padding equal to same. So we have done this 4 times. So the size will like become half, then 1 by 4, 1 by 16, 1 by 32. And then if you do this con 2D transpose, so like equal number of times, if you do as many number of times you have taken it down, so that will make your this will upsample your image. So like you first go down, so reduce the size of the image and then increase the size. So then, yeah, that's our that's what our network is. And so this function get model, in this function get model, you will give the image size and the number of classes. So you can see we have 3 classes here from this example: 0, 127 and 255. So yeah, we give this input as the number of image size and the number of classes, and model.summary gives us the summary of this model. So then we'll set aside some data for validation. So we are taking 1,000 images for validation, and so you can see we are saying train image input image paths equal to input image paths, so from 0 up to minus val sample. So you remove the last 1,000 images from the data for validation. So you keep the input and target, that input and target data for validation, and then you instantiate the data generator. So you say train gen equal to Oxford pets, batch size, image size, train input image paths, and train target image paths. And similarly, you create the validation data generator. Now, after creating the validation data generator, we will compile the model. So we say model.compile, optimizer is RMS prop. So if you remember, we already discussed what RMS prop is. And so RMS prop and momentum, it gives us the Adam optimizer. So but in this one we are using only RMS prop. And loss function is sparse categorical cross entropy. So in this one you can see this training generator. So we have, yeah, so we had this training data generator, and in which we created this x, so which will fetch you the x's and the y's, so which are the input and the target. So you are basically just loading this image. So it says, yeah, so this image img equal to load image, and you give the path, and the target size is this one, and xj is equal to img. So from the tensorflow.keras.preprocessing.image function, this load img, this will return you, I think this will return in a tensor. And then you also do the same thing for uh, for the target. And so the ground truth labels, so you generate the ground truth labels from them. Now we will see once our data generator and the validation generator have been created, we will see how to, okay, yeah, for sample in train gen, or we will say train gen dot, we will get an item from there. So we will say dot get item one. Oh, we're not supposed to get that. So this one, it returns, let us see what is the shape of this. So this will return us an x test comma y test equal to. So let us extract one single sample from this. and we will just see what is there in the data. It's always very important to check what is there in your data. So you have a batch size of 32, 160 by 160 by 3. Okay, similarly, you have y test dot shape. So you can see here you have these labels, and y test, the values, so you can see, are going from 0, 1 and 2. So y test dot max is 2, and if we just check the type, looks like numpy. Yeah, this is a numpy array. So then you can see, okay, so we will use callbacks here. So Keras, yeah, tf dot Keras dot callbacks. So what you will do is, so you will say best only equal to true. So at the training time, we will check with the, so we will not give the, we will build the model using the training data, and while training we will check the performance using the validation data, and the best model that we will get at any particular epoch, we will save in this file oxford segmentation.h5. And so this is, so we have to pass this argument callbacks, and we have to say these, we have to give these callbacks for doing different things like early stopping or saving the best model. So let us run this, and let me check if we are running on GPU. Oh, no. So we are not running this on the GPU, so this will take a lot of time. Let us change the runtime. GPU. Okay. Anyways, so this will fit the model. So model.fit will train the model, and then we can do visualization. Let us, okay. So this is going to train our model. This will take a lot of time, seems. So then we have, okay, while this runs, we will start maybe with the next example, which is 3D image classification from CT scans. So you can change this to 3D image classification from radar data, from numerical weather prediction data. And so this example will show the steps needed to build a 3D convolution neural network to predict the presence of viral pneumonia in the computer tomography scans or CT scans. So 2D CNNs are most commonly used to process the RGB images. A 3D CNN is simply the 3D equivalent. So it takes in as input a 3D volume or a sequence of 2D frames. And 3D CNNs are powerful model for learning representation of volumetric data. So let us see this how much time this will take. Take some time. Okay, we can go through this in the meanwhile. So first is, yeah, so you import these things from TensorFlow and TensorFlow.keras, and then you download this MOS data. So these are chest CT scans with COVID-19 related findings. So let us see how this data looks like. Yeah, so this looks something like this. So these reds are what I'm assuming are the is the pneumonia. So we'll download the dataset from datasets. So this is the URL, and yeah, this is downloading the data. Yeah. So these files are provided in Nifty format with extension NII. So this might be some format for the CT scans. And to read the scans, we use the Nibabel package. You can install it via pip install Nibabel. CT scans store raw voxel intensity in Hounsfield units. So they range from -1024 to above 2000 in the dataset. And above 400 are bones with different radio intensity. So this is used as a higher bound. A threshold between -1000 and 400 is commonly used to normalize the CT scan. So to process the data, we do the following. So there is some basic data pre-processing that is specific to the domain. So that is being performed. And they first rotate the volumes by 90-degree. So rescale the values between 0 and 1, resize the width, height, and depth. So to read this data, you read it using this NIV library, and it returns this scan. So then they are normalizing the data. So this is you input the volume. If it is less than min, so you assign min to it, and if it is greater than max, you assign max. Otherwise, vol minus min by max minus min. And then you resize this data set, so the desired depth, width, and height. So resize it into like a common uh, height, width, and depth for the entire data set. So yeah, so for that we will use this nd image, which is from SciPy. So we are first rotating this by 90 degrees, and then it says zoom. So by what is the factor by which you want to zoom, and then so this entire process. So these three functions: read, normalize, and resize. So you just give the path of the image. So this will do for you. And then the folder CT0 contains the CT scans having normal lung tissue. Okay, we'll see this. So it's inside this MOS metadata. So CT0 consists of CT scans having normal lung tissue, so which does not have, so no CT signs of viral pneumonia. So these are the images which do not have any pneumonia. And folder CT23 consists of CT scans having several ground glass opacifications involvement of lung parenchyma. And okay, so let us see CT scans with normal lung tissue and CT scans with abnormal lung tissue. So then we will build the training and validation data sets. So the abnormal scans we will say equal to np.array process scan. So we pass this function process scan to path, and for path in abnormal scan path. So what is there in abnormal scan paths? So seems like a list of file names. Yeah, so this is a list of file names with all the abnormal scan paths, and these are the normal scan paths. So you are reading them, reading these files and converting them to Numpy array. So we'll see if this is run. Not yet. Now we basically want to build a classifier for this 3D data, wherein if we just input the new 3D CT scan, the model should tell us whether the person has a COVID-19 related pneumonia or not. So then we will create these abnormal labels. So this is np.array equal to 1 for I, for you don't need an I. So for range length, so you just create an array of 1 and an array of 0, and then you have these the extrain. So split the data into a ratio of 70-30 for training and validation, and you concatenate equally from the abnormal scans and the normal scans. So first 70 images or 3D dataset from the abnormal scans, and the next 30, next 70 from the normal scans. So that is your X train and your Y train. So Y train will consist of the labels. So you concatenate these data sets and concatenate along axis equal to 0. And then we have the validation data set, which is the rest of the 30% data set. So now if we will just see the shape of these abnormal scans. Yeah, this is taking some time. Anyways, this training is complete. So now in this example, we will so we have this validation data generator, and you have the validation predictions, and so we will print the results. So you can see here we have this you have this input image, and you have this target mask. So this is the ground truth mask, and this is the mask predicted by our model. And okay, so the thing is our model sees only inputs at 150 cross 150. So our prediction looks somewhat reasonable. It's not doing good here. It's predicting zeros, whereas it should be one. But more or less, in a broad sense, it is doing a good job. And then let us see this example. So this is still running.
Sir,
Yeah.
does this code have done edge detection of that input image?
Which one? The
Uh,
segmentation code.
yes.
Yeah. So you can see it's doing the edge detection, right? Not
Yes, sir.
perfect, but still it's doing a reasonable job at it, right? But for that you need this kind of input and target label dataset.
Sir, this third image is generated by model, and how
Hmm.
the second image is generated?
This is the ground truth. This is the actual value, like corresponding to this image. Oh,
Okay.
the mask, the label. So here in the center you can see he. I mean this is another a different object, right? This
Yes.
bone that is hanging. So yeah, and then this is the dog. So yeah, this is the actual ground truth that it should have predicted, but it has predicted. It looks like a chicken. Yeah, anyways. So
Okay.
yeah,
Okay
I mean
means
it
this neckband it should detect it as another object and dog as a one object.
ideally no. So the thing is, so this has been labeled, I think, by humans only, or somebody must have labeled it, or they must have used some algorithm to label it. So you can just label this entire thing as a dog. That will make the task easier for the
Yes.
model to learn. Yeah. So that's on
Yes,
you. I
sir.
mean, you can generate your own labels.
Yes. Means I think with edge detection it will be more easier because it will simply outline the
Yeah, yeah, yeah.
entire. Okay.
Edge detection will be much more easier, I think. Yeah, yeah, you're right. You're right. You just have to tell the edges, which yeah, edges it is able to tell. Yeah, you see this? Like maybe not the ears which are protruding out, which is a fine detail. I think if you train this model, so this model was trained only for 15 epochs. If you train it further, yeah, this will basically even detect fine edges. Not an issue in that.
Is it taking 1000 input images by the models?
So this is taking. Let us see how much. You mean the 3D image classification or this segmentation problem?
The first
Okay,
image
yeah.
segmentation problem.
Yeah.
I
Let
think
us see.
1000 images are taken for validation.
1000 is for validation, I think. Yeah.
Yes, sir.
1000 is for validation, but there are more, I think some 7000 for the, yeah, we'll have to see. Yeah, so there are more images for training.
So the
Ah,
objective of this model is to do image segmentation, right? Means
yes. So every pixel, you have to classify every pixel in this. Now this problem, the second problem, this is you have these CT scan, okay, 3D data sets. You have to just tell whether there is pneumonia or not. This is a
sir,
classification problem. This is not a segmentation problem.
in the
Yeah, yeah. Please go ahead.
in this second example, that is CT scan images,
Yeah.
input information is 3D data. So what are the three dimensions of that data?
Okay. Yeah, you have the data set in X, Y, and Z, no? So the dimension
Is
is
it
128
how,
cross. Sorry.
is it height, width, and depth of that?
Yeah. So it is, yeah. So 128 cross 128 cross 64. That's the. It's
Okay.
like a cubical. It's like a cubical data set.
Is it okay? Means height, width, and depth of the brain,
Yeah.
and it is
Yeah.
scanning all those tissues and finding. Is it finding the defected tissue with pneumonia?
No. It is not. So it is not doing segmentation.
Okay.
Okay. So you are just. So you have. Okay. We will. We have two folders here. Okay. CT0 and CT23. Now in one of the folder you have all the data sets which are, yeah, so the CT23 has all these scans which are which have got some kind of pneumonia, whereas CT0 are all normal scans. Okay, so you just read these 3D data sets, okay, CT0 and CT23, label these as 0, label these as 1. Build a model in which you will then input a 3D CT scan, and that model will tell you whether that CT scan has a pneumonia or not. Now,
Okay,
where
means
it is
model.
becomes a 3D segmentation problem. That is, yeah, you can even do that. There's no problem with that, but you need the exact labels. So you first need to generate the labeled data set. So at every grid point, you just need to label maybe 0, 1, or 2, something you need to label.
So means in this example, we can say that it is the basic model in which it is comparing two sets. One
Yes,
is normal tissue and another one is infected tissue. So that
yes,
model is itself is predicting the defected and the normal.
yeah, that's what the model
It
is
means
doing.
depending on training, it was taking decision.
Yeah. So this is yeah. So the training you are doing in such a way that you are giving it equal number of normal and abnormal tissues. So you are giving it a balanced data set, and it is learning to identify, like, or to classify whether CT scan is normal or abnormal.
Yes, actually, what I want to say that I understand the concept of this model means we don't need to get into the details of that biology portion of that issue.
Yeah. I mean, that's on you. Okay. I mean, if you are exactly trying to find out where that abnormal tissue is, then you would need to do the segmentation, right?
Yes.
Yeah. So, oh, this ran. Nice. Okay. So we will do the data augmentation here. We will quickly see this model. Uh, okay. So these are the different these are the data sets, the 3D data sets shown from the CT scans. And now in this case, so you can see here, we are building a 3D convolution neural network. And so the input here will have you will have width, comma, height, comma, depth. Okay. And so you will say, so we are using this con 3D, and you give the filters. We have 64, kernel size is 3. So now this is a 3D kernel, so it's basically 3 cross 3 cross 3. And you have ReLU activation, and you pass this to the inputs, do a max pooling 3D and batch normalization. So this will keep reducing the size of your input data. And then in the end, you can see we have a dense layer. So this dense layer is having 512 neurons, and you also have a dropout layer. So with you're basically dropping 30% of the nodes. And the output is eventual output is a dense layer with just one neuron. Activation is sigmoid. So this will basically give you just a 0 or a 1, and you then define the model. So Keras dot model inputs, comma, outputs, and you can even name this model. So this is your 3D CNN. And just like we have created this, the so you compile the model, so you have to give a loss function. So here we are having this binary classification problem. So it's a binary cross entropy loss, and we are using the optimizer as Adam optimizer with a particular learning rate. And you just also keep checking the metrics, and you also use something known as learning rate scheduler. So in this learning rate scheduler, you have this initial learning rate, which is 10 to the power minus 4, and at every 100,000 steps, So you have a decay rate of like 96%. Okay, so you just keep reducing your learning rate every 100,000 steps or every 100,000 epochs, and then you also save the best model. Okay, and also we can apply this early stopping. So you see here we have two callbacks. So these are the different callbacks. So we have the early stopping callback and the model checkpoint callback, and we pass them as a list inside the callbacks argument. You can see callbacks equal to, we are passing this as an argument. So you say model.fit train dataset. So this train dataset is your data generator, and you give the validation dataset. What is the number of epochs, whether you want to shuffle it or not. So yeah, you can then see the loss, and you can make prediction on the single CT scan image. And so you can also print the values, sigmoid values, so which can give you the percent probabilities of, or the confidence that what the model is predicting. So for example, you give this model some images, and or these are 3D images, so the model will say, okay, this is the percentage of confidence that this CT scan is normal or abnormal. Then okay, it's 3 5. So we will see these other examples in the next class, and yeah, that's it for today. So is Friday, yeah, Friday is a holiday, right?
Yes, sir.
Yes, sir.
Okay, so we will meet on Monday then.